In Chapter 4, we're going to talk about systems, specifically things within the Earth systems area. We will start off with these particular areas. We'll talk about basic systems, how systems respond from input, and the type of flow that they will have. We'll talk about the concept of overshoot and collapse. Also discuss irreversible consequences. And then terms such as environmental unity, uniformitarianism. That's a mouthful there. We'll talk specifically about Earth as a system and the types of changes that can occur within these systems. So let's talk about just some basic concepts of systems. You already have a pretty good idea of what a system is. It's basically, if you were to look at your human body as a system, it's made up of components. So you have the endocrine system, which I believe is skin. You have your pulmonary, your heart and lungs that make up part of your body. That's part of the system. The cellular level is part of your system. So there are things, you can think of it best, I believe, as just components that make up something. And in what we're looking at, we're talking about environmental science, we're talking about the Earth and the types of systems that occur in the Earth. Now, when we talk about systems, we will discuss open and closed systems, and basically for the Earth itself, if we were to look at the Earth as a whole, it's basically a closed system, and I'll explain why here in just a moment. But a lot of the systems that we look at, especially in the environmental sciences area, are open systems. And so what we mean by that is that energy, and again we'll talk about what energy is later in this course, but for what we're looking at here, let's look at, for example, the sun, the radiant energy from the sun. That crosses various boundaries within different components of the Earth, or any type of material. But I'll explain this a little bit more in depth here shortly. So as of this part of the video, just realize there are two types of systems, open and closed. Now let's talk about what we call a static system. It's basically a fixed condition. In other words, whatever state that system is in will stay in that particular state. So the example in your textbook talks about a set of balloons attached to a pole, and unless you cut the balloons or unless you cut the string that ties it to the pole, the balloons are going to stay on the pole itself. So it's not leaving that particular state. When we talk about balloons on a pole, we're talking about a static system. For instance, in the Earth's atmosphere, we have parcels of air that rise from the Earth's surface up into the atmosphere. Based upon the stability of the Earth's atmosphere, will basically air parcels will move up or down. There's actually a better example of this, and I'm going to show you an example here. So the example here of a stable system, a static system, would be this individual pushing this rock up the hill. Now what the individual is doing is taking the initial state of this particular rock and changing it from the valley and pushing it up the mountain. If this rock were to move back down to the valley, then we would call that a static system, or basically a steady state system. Now in terms of dynamic systems, you give it an initial push away from something and it moves off. So if we were to go back to this example where the individual is pushing the rock up the mountain and the individual is successful getting the rock to the top of the mountain, it has now moved away from its initial condition, which was down in the valley, now moved up, that's what we call a dynamic system. It changes, and it changes over time. In your textbook, it uses the example of a hot air balloon. Actually, the Hot Air Balloon Festival in Indianola is something that my wife and kids, we attend that every year. And you see the beautiful balloons that initially launch, and the initial state of that system. If you think of the balloon as a system, in other words, the components of that air balloon is the actual balloon itself, the furnace, which provides the heat source, the compartment, the box, where you have the riders in the hot air balloon. So these are all parts of the system of the hot air balloon, and as they provide heat to the balloon, we know that hot air or warm air is typically less dense compared to cold air, and so the balloon begins to move away from the ground and moves up into the atmosphere. In other words, we say this is a dynamic system. It moves, it changes over time. Now, if we look at this particular setup here, you've seen this before, a grandfather clock, and you've got the pendulum down here that swings back and forth. But let's say for this example, the grandfather clock is broke, so the pendulum is no longer moving. If you were to push the pendulum itself, in other words, you were to disturb it from its resting state, it would begin to move back and forth until the energy that you provided by moving that pendulum begins to be depleted, and the pendulum goes back to its initial system. We would call that a steady state type of system. Now, the concept of dynamic equilibrium is basically something that all areas of nature tries to move toward. In other words, it becomes its original. So now that we have an idea about the different systems concepts such as static and dynamic systems, and I've talked about the classical system being the pendulum, let's look at a concept called dynamic equilibrium. And it's often painted, for instance here this is a painting from 1858 called Morning in the Tropics, and it's supposed to represent an environment that is unchanging or changing extremely slowly. And so the idea out there is that Earth systems or components, compartments of the Earth system is not changing. However, and when this is occurring, we call this the dynamic equilibrium. So systems are moving to a point of equilibrium without the influence of people. This is true for short periods of time, but as you're aware, things change in the environment. Ecosystems change. So the idea of dynamic equilibrium, especially now that we have people involved, changes the environment. We'll come back to that here in a few minutes. So what I want to do now is I want to talk about a simple budget equation. And you'll see why we're going to use this here in a moment. But the equation, a simple, straightforward equation, I is equal to O plus or minus the change in S. And keep in mind, we're talking about systems here. So think of this as some sort of compartment. You can think of it as your bathtub. In fact, the bathtub would be a great example. Input for a bathtub would be the spigot, and the output would be the drain. And so based upon, well, let's just assume that the input and output are equal. In other words, they're in equilibrium. So whatever you're putting into the spigot is the same going out and so therefore you would not have a change in the water level. However, when we take a bath, we want input greater than output, because if we have more water coming in than leaving, then the level, the change in storage, as this is defined, will begin to increase. And we can rearrange this equation to look at the change in storage is equal to input minus output. So if we do that, just a moment, let me bring this up here. Give me just a moment. So if I rearrange this particular equation, give me just a moment. This is simple algebra. I is equal to, like I said, output plus or minus delta being change. Let's see, how can I represent delta on a keyboard? I will just put change in S. So I can rearrange this and say that the change in S, the storage, in this case our bathtub as an example, is equal to input I minus output. So if we want to increase the storage, we increase the input, which is the spigot, minus the output. And at the end of the bath, you want the change in storage or the water level to decrease. So at that point, you would want your output greater than your input. So now the storage begins to decrease. Your textbook uses an example of, I believe, what was it? I'm trying to think of what they used for an example. Number of college students coming through. And in fact, so they said that, I'm sorry, I'm having a hard time remembering exactly the example they used, but let me just jump ahead here. I don't want to. You can read it in your textbook. But let's take a look at this input and output. And so in the example here, you'll notice I've put in here a repository. You can think of this as a tub. There is the output valve, which is the spigot in this case. And then you see the water level here. If I were to put more water into this tub or this basin than what is going out, the water level would increase, as you see down here in this example. So in this example here, I'm putting more water in than what is going out. The water level increases this. Same thing as a bank account, your checking account. You put more money in than you spend, the amount of money begins to increase. So this is a very simple equation that talks about input into some system. One example your book uses, and we'll get to here in the next slide, has to do with river basins, those types of things. So if we want to, I'm just beating a dead horse here. I think you get the idea. So let's move on to the next slide. And in this particular case, we're talking about a steady state system. And in a steady state system, recall that input is equal to output. So this is just another component of a system, an example from your book that talks about average residence time. So again, in a steady state system, in other words, the system is not changing, the input is equal to output. So when we talk about this concept of average residence time, basically what we want to find out is how long on average a quantity, in this particular case, water, will remain in the reservoir of a system. And the equation for that, ART, the average residence time, in other words, how long something will stay in a particular system, is related to the size of whatever you're using. In this particular case, we're using Big Lake here as an example. So the size of this reservoir, if you look at this, holds 1 billion meter cubes of water. So it's a rather large reservoir. And F is the rate of transfer. So when we talk about the rate of transfer, we're talking about input and output here. Okay? So S is the size of the reservoir and F is the output. Now one of the examples they used here is a chemical called MTBE, which when it gets into a lake or a river is a pollutant. And so they want to know, if you have MTBE coming into the lake here, how long will it take to propagate through the lake until it eventually reaches the dam and moves on? So we can look at that here in just a moment. But notice here, you've got several inputs into this lake. You've got Bear River, which puts in 6 meter cube per second of water. So 6 cubic meters. Recall that when we're talking about anything cubic, we're talking about volume. So we've got 6 cubic meters for every second running into Big Lake. And so we've also got the Ox River draining into Big Lake, and its input is less at 3.5 cubic meters per second. And then Cat Creek also feeds into this large reservoir called Big Lake at a rate of about 0.5 cubic meter per second. So if we take a look at all three of these inputs, we add them together, 6, 3.5, and 0.5, the total input into the system, and we're talking about the system is the lake, Big Lake, is 10 meters cubed per second. So they're getting 10 cubic meters of input into the lake. Now notice what it says here also. It says the output, okay, from the lake into the dam, out of the dam, is 10 cubic meters per second. So notice here that input, the 3 different rivers going into Big Lake, is equal to 10 cubic meters per second. And the output out of Big Lake is also 10 cubic meters per second. So the water level is going to stay the same. Okay, input is equal to output, which defines a steady state system. You know, you go back here to this example that I used. In this particular case, in this top picture here, input is equal to output, so there was no change in the water level. However, if output is greater than input, which in this case, then notice the water level began to decrease. And then input here being greater than output, the water level increases. But for a steady state system, input is equal to output. So what we can do, use a little bit of math here. We want to figure out how long it takes, okay, the average residency time for Big Lake. Okay? So we recall that, so we're talking about water going from here to here. So how long on average a quantity of something will remain in the reservoir of a system? So notice here we've got the S, which is the size of the reservoir, which is 1 billion cubic meters, divided by the flow rate. And again, the flow rate coming in is 10 from these 3 inputs. So it's 10 cubic meters per second. And so now we see that when we do that, the average residency time is 100 million seconds, or 10 to the 8 seconds. And then you can do conversion factors here. So if you've ever done it, we know that there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year, and so we end up with units of seconds per year. So we see that the average residency time for Big Lake is roughly 3.17 years. So a shade over 3 years it takes for water to move through this reservoir. So the question is, why do we care about average residency time? Are we just doing math? Well, I took this particular screenshot out of your textbook because it talks about if we have a fast input and output, okay, if we have fast input and output into a reservoir, then the residency time begins to decrease. So in other words, If we were to increase the input here on this, so we've got the size of the reservoir versus the flow rate. So it's a simple fraction here. If we were to increase F, increase flow rate, then the average residency time will begin to decrease. So right now our average flow rate is 10 cubic meters per second. If we were to increase that to 20, 30, 40, 50 cubic meters per second, then the average residency time, the time for the water to move through the system, will decrease. So what does this mean in terms of environmental science? Well, let's say you have a pollutant, such as an MTBE. Okay? So in this particular case, MTBE, if we assume it moves with the flow rate of the 10 cubic meters per second, it takes roughly 3 years to move through the system. So if the flow rate increases, that means the MTBE will move through it. In other words, its average residency time will decrease, okay, because F is increasing. Remember, when the denominator increases, then what you're looking at, the component you're looking at, will begin to decrease. There's an inverse relationship there. So if we increase the flow rate, then the time it takes for a pollutant such as MTBE will go through much more quickly. However, as your textbook points out, you look at oceans, and so they have inputs from subsurface water, runoff from snow melts from mountains, streams that feed into oceans, precipitation that falls into oceans. Oceans are large, and typically the flow rate out of the ocean or into the ocean is smaller. And so if you get a pollutant in an ocean, then the pollution hangs around for a longer time. So the average residency time is a very important concept, especially when we're talking about pollutants. So let's talk about stability or steady state. We said that a stable system is within a system remains, if it's stable, then what we say, it stays in that condition until some sort of energy is added to it to perturb it. And if we begin to add some energy to it, so for instance, let's go back to this example here of the pendulum. The pendulum is initially standing still, it's in a steady state. However, if I impart some energy, in other words, I take my hand and begin to move the pendulum, it begins to move left and right until the energy is dissipated and it returns back to its initial state, assuming I don't push it again. So when we talk about a stable system, it is in a condition that remains the same unless we disturb it. Now, when we talk about steady state or stable systems, is this a desirable thing to have? We'll talk about that too a little bit later in this particular module. But the thing that you need to realize is that steady states in the environment, in different components that make up the Earth system, rarely stay steady for a very long period of time. There's usually some sort of outside influence acting on it that can create issues. Now, when we talk about these outside influences acting on systems, what we're talking about is feedback. So let me spend a moment here and talk about feedback. Now, feedback we define is when there are changes to the system that affects other parts of the system. So for instance, we have input and output. Right now we're just talking about the simple model of input into a system versus output. So if there's a change in input, there will be a corresponding change in output. So what happens? The output feeds back into the input. Now there are two types of feedback, one called negative feedback and the other called positive feedback. And I'll provide some examples here in a moment. But you see there on the screen, we talk about negative feedback. An increase in output leads to a later decrease. In other words, it's self-regulating or stabilizing. And in some cases, a negative feedback, actually in most cases, a negative feedback is desirable in the environment. Now with a positive feedback, if we increase the output, this leads to a further increase in the output. So it's a destabilizing type of issue. So if there is an impact to the output, basically what you end up creating is a runaway train. And typically you see environmental damage when we have positive feedback. Now this doesn't mean that all positive feedback is a bad thing on the environment. But let me give you a couple of examples that might begin to help. In fact, I'm going to jump down here a moment. Your textbook gives an example of positive feedback in the form of all-terrain vehicles here. Actually, it's not an ATV here, but so what you begin to have here is at one point, you see the shrubbery up here. It was down here as well. But as these vehicles begin to traverse, they begin to uproot, they begin to tear the shrubbery from its roots. It begins to die. And so now you begin to have what we call desertification. In other words, the beginning creation of deserts. And so what ends up happening when you begin to expose more and more of the Earth's surface, the soil, the sand, then you have more erosion. And so what ends up happening is that you begin to get these tracks. And in some cases, they develop into deep ruts. And obviously, these vehicles here begin to avoid the deep ruts and begin to tear up more and more of the vegetation. So the output is basically creating more desert, more erosion, and this continues to increase the loss of vegetation. So over time, as this part of the track becomes impassable or dangerous for the vehicle, they'll begin to move up into other areas as well. Now there's also an example. Well, let me give you an example in terms of meteorology. So we talk about global climate change, and in one aspect of global climate change we talk about global warming. So in an environment of increased carbon dioxide, you've probably heard this, that CO2 is what we call a greenhouse gas. So the more greenhouse gases that you get in the atmosphere, and we'll learn how this works later in this course, but with an increase in greenhouse gases such as water vapor, CO2, then temperatures at the surface begin to increase. Well, what ends up happening as the temperatures begin to increase, we have more evaporation of water. And when we evaporate liquid water, it turns into water vapor. That's water in the gaseous state. Water vapor is a much more powerful greenhouse gas than CO2. We typically think of carbon dioxide because that's what we hear a lot about. And carbon dioxide is a big player in warming. It is a greenhouse gas. But in the example that I give, water vapor is increasing, and when we increase water vapor, we increase temperature, which begins to increase even more evaporation, which adds more water vapor. So you see what we're doing there, we're increasing the output. In this particular case, we're increasing water vapor, which means then we're increasing the temperature of the surface, which in turn increases more evaporation. So it's a runaway train here. So that's an example that you're probably familiar with. Now, the example in your textbook talks about the development of city populations. And in this particular case, what we have here is both positive and negative feedback. So what you see here in the particular slide here, as cities begin to grow, you begin to develop more jobs, healthcare begins to become more accessible, better. There's social services offered because you have more people in, a higher standard of living, which attracts more people into the system, which increases the city population. And so that is a feedback here, a positive feedback loop that is good. Now notice I talked about earlier positive and negative feedbacks. I said in some cases, positive feedback to the system is a good thing. And in this particular case, it is. However, this at the same time produces what we call negative feedback to the system. In this particular case, the system is the population of a city. So as we begin to increase jobs, healthcare, social services, industry, we begin to increase air pollution. There's more people available, more cars, more industry. Anytime you begin to pack people together or increase the size of a city, you have more diseases, more crime, increased traffic. So then people want to leave the city. They want to move back to the country. And so then your city population begins to decrease. So if your positive and negative feedback are equal, then the population doesn't change. So this is an example of how, in nature, both positive and negative feedback actually work together. Now what I'd like to do is talk a little bit about flow in systems. There are two types of flows. Now when we talked about flow, one of the things that we were talking about here back in this example, we were talking about flow, input into the system of water from various rivers feeding Big Lake. But what we're going to talk about here is a little bit different. Concept of what we call linear flow, nonlinear flow, and then we'll talk about the concept of lag time. But a great example of linear flow is this particular graph in your chart, in your textbook. We're looking at population in millions versus years. And so we're talking about U.S. population. The assumption, as U.S. population started at 2.5 million in 1776, that number kind of blows me away. I have a hard time picturing 2.5 million at the beginning, back in 1776. So the blue line, so if we assume that population begins to increase at a steady rate, you begin to see population increasing with this blue dashed line, a very linear type of increase. And so from 1776, if you assume a linear growth, then you end up, looks like here at about 75 million around the year 2000. Okay. So we're assuming 250,000 people added each year to this total. Now obviously this is not a true representation of our growth here. So in this particular case, what ends up happening if we look at nonlinear growth, in other words, not a nice line here, but nonlinear growth, it begins to increase slowly. In fact, it lags the linear growth. Notice that the red curve is actually below the blue. But then it reaches a certain point where it begins to take off and begins to increase rapidly. So in this particular case here, it's saying 750 million in the U.S. So what is the difference between the linear growth and the nonlinear growth, other than the values, the difference in values there? Let's talk a little bit about this. So linear flow, we add the same amount each year to a system. However, with nonlinear flow, it changes. And so I'm going to talk a little bit about an example here with what we call exponential growth. Kind of jumping around here, but exponential growth is represented here by this red curve. And so when we're talking about exponential growth, it involves two factors: the rate of growth measured as a percentage, and something called doubling time in years. In other words, how much time passes before the quantity we're looking at doubles in size. Exponential growth is a positive feedback. So, in other words, as we increase the output, in other words, the growth, that also increases the input and makes it very difficult to have what we call a sustainable environment. Recall in the previous chapter, I believe it was chapter 2 or maybe it was 1, we were talking about sustainability. In other words, the ability of the environment to provide for its population without creating issues on what is being provided by the environment. There actually, let's see, in the slides I do not have this, but there is a formula for exponential growth for what we're doing in this particular course here. I want you to realize that with exponential growth, it begins to take off very quickly. It's actually, you can equate this exponential growth to the stock market, or if you have a savings account, and let's say you start off, I don't know, with $1,000, and your rate of return, let's say, I'm going to be ridiculous here, but your rate of return is 20% after 1 year. So with 1,000, let's see, I'm going to do this off the top of my head, but with $1,000, at the end of the year, if you have 10% growth on that, you add an additional $200 to that $1,000. So the next year you start off with $1,200 and the rate of return is 20%. Then you're adding another $240 on that. So as time begins to pass by, it begins to increase rapidly. Now I'm not even talking about compounded interest, but I'm just talking about interest in itself. So we're talking about percentage of growth and a time when we're talking about exponential growth. And when we're talking about linear growth, we're only talking about adding a certain amount, in this particular case, 250,000 to the population each year. Now, it's also very possible to have what we call a negative exponential curve. So in this particular case, we're looking at mortality rates. In other words, the number of individuals by their longevity. Let's see. So you've got this particular curve here, which is your typical negative exponential decay. Notice we're going from the number of individuals as we go older, as they begin to age, the number of individuals begins to decrease rather rapidly. The green line here is age-dependent mortality. So the maximum age they start off here is with 30. The initial mortality rate is 7%, and the average increase in mortality is 1%. So the initial mortality rate of 7% is increasing each year, which leads to an even larger decay in the number of individuals as you begin to age. So when we're looking at systems and beginning to quantify systems, we look at them in terms of linear growth, exponential growth. You can also have negative linear growth, although your textbook doesn't talk about it. But we also have negative exponential growth as well, or it's more like decay. It's an oxymoron, negative growth. So we're going to call that decay. Also, I believe it was in chapter 1 or 2, we talked about the saturation curve. We talked about CO2 being uptake by a plant versus the amount of light hitting it. Recall that photosynthesis requires light to a living organism. We'll talk a little bit about that later when we get to chapter 7. But you notice here for soybeans, as we begin to increase the amount of light. Okay, so now we're talking dependent versus independent variable. So if we look at light intensity, if we're changing the light, then that means the net CO2, or the photosynthesis, is the dependent variable. Okay, So the rate of photosynthesis is dependent upon the light, how many foot candles of light. So it's like 1,000 candles per foot, and so you see that CO2, net CO2, increases rapidly until it reaches a certain point of light. So if you have 3,000 foot candles, you get very little increase. Whereas with the shade plant, it doesn't take much light before the net CO2 uptake or the photosynthesis begins to stabilize. So we've talked about several curves here when we're looking at Earth systems. Another one, and this is a key one that I want to spend a little time here on. So we're talking about time, so T1 going into the future, T1, time 3, time 4, time 5, time 6. So time's increasing on the x-axis, and population goes from low to high. And so when we talk about nonlinear flow of population growth, and by the way, I'm going to add Chapter 5 into this course. It's on population. We talk about population a lot early on in this class and the effects that population have on things such as biogeochemical cycles, which we'll talk about in Chapter 7, energy, which we'll talk about in later chapters, and also global climate change as well. So it's critical, I think, to have an understanding on population dynamics, and we'll talk about that when we get to Chapter 5, the next chapter. So initially I didn't have that included in this course, but as I'm looking at this, I think it's important that we learned concepts related to population. So we have nonlinear growth of a population, so you see it here, the blue line beginning to increase rapidly. And then you have this other line called carrying capacity. Recall from the previous chapter we talked about carrying capacity. In other words, the ability for the Earth to provide a sustainable environment for a population. So notice that carrying capacity is quite high here initially, and as long as the population growth is below the carrying capacity, then the Earth can provide for its population. But we come to a point, now notice carrying capacity is not changing because it's able to handle what population that we have at this point. So the inputs and outputs of the carrying capacity is the same, so it's staying level, but we reach a point where they become equal. And once the population goes over the Earth's carrying capacity, or the Earth's ability to provide for its population, notice then that the carrying capacity, in other words, the sustainability, begins to decrease rapidly. So the Earth now, what it can provide support for a population decreases rapidly. And notice for a while, the population still is increasing. So now we're at a point where I have the crosshairs where the population is greater than what the environment can provide for. So what ends up happening is that now the population begins to decrease. So now, we talked about the 1970s and 1980s portions of Africa where starvation was going on. What had happened is that the population grew to a point where the resources there in Africa could no longer provide sustainability. And so you begin to have death occurring. And so now you have this rapid collapse in population. And in fact, it's a more rapid collapse than growth. And so now we have a negative exponential growth to population. And eventually it will reach a point to where, once again, what the Earth can provide in terms of carrying capacity, okay, in other words, what it can provide sustainability, is equal to the carrying capacity and population. Now, once the population begins to dip below this carrying capacity, then population will continue to decrease. Now, you would think, wait a second, if the carrying capacity, what the Earth can provide, is greater than the population, shouldn't it begin to decrease? But there's this thing we call lag time. And so the population will begin to will continue to decrease until it reaches a point where it begins to stabilize, and then with time begin to increase again. But there's what we call, now lag time is an important concept as well. It's the amount of time it takes for the consequences of something going on in the environment to negatively impact what we're looking at. So in this particular case here, seems like growth is great, but then, and notice here we have this growth still occurring even though the environment can no longer support the population. There's a lag in time before the population begins to decrease. And then we see this lag in time again before the population begins to increase, even though the Earth here can provide more than what we have in terms of population. So this is what we call overshoot. This is the point where the growth overshoots or exceeds the carrying capacity. And so this is an important graph, especially in environmental science, and it has applications beyond population, and we'll talk more about that. Now, there is a term called environmental unity, and basically what environmental unity means is that it's impossible to change only one thing. In other words, if we were trying to, I'm trying to go back to an example here. So the idea behind this is that the Earth and everything within the Earth, its different ecosystems, the biosphere, all of these type of things are interrelated. They're connected. So a change in one thing will begin to have impacts in another. So for instance, let's just use this example that you see right here. So now you see quite a bit of erosion. Notice that there was a lot of forest here, and here you see quite a bit of shrubbery here, grasslands, more forest. But what ended up happening is that they begin to clear out some of the forest. So keep in mind, this erosion, this wearing away of soil, actually at one point was the same level as the grasslands here that actually house the trees, the forest. But what happens, you begin to pull the trees up, it begins to pull the roots out, you expose more of the soil, so you begin to have erosion, and the more erosion that you have, you begin to create these craters. Now think about this. Now that you've got severe erosion, you have severely impacted parts of your system, your Earth system, your what we call ecosystem. Now what happens with that is that now you have exposed ground here. And the exposed ground is taking in energy from the sun, and it's literally baking it. It's drying out any type of moisture that was stored in this part of the erosion. And we know that plants, shrubbery, grasslands, trees need moisture. So what ends up happening is the fact that you clear out forest, the clearing out of the forest begins to promote erosion. The erosion exposes the soil to energy from the sun. The sun begins to dry out this area, and it's difficult for plants and vegetations and forests to begin developing again. And in fact, what also ends up happening is that when we begin to remove the trees, keep in mind that trees are a great what we call sink for carbon dioxide. So like we breathe in oxygen and we expel CO2 or carbon dioxide, plants do the opposite. Trees do the opposite. They take in CO2. They remove CO2 from the atmosphere. So what we're talking about with environmental unity, the idea originally of taking some trees, knocking some forest out, created severe erosion, which impacted growth of future grass, shrubbery, because of input from the sun. And now, since we've removed trees, we've now removed a source of removing CO2 from the atmosphere. So small tweaks in the Earth system has huge implications, some negative, some positive, to the environment. So that's what we mean by environmental unity. Now we've got another concept here called Uniformitarianism. That's a mouthful. I had to practice that one for a while. Uniformitarianism, you see there, was suggested by James Hutton, who's the father of geology. And basically what James Hutton said is that the processes that have happened in the past, the processes of mountain building, the processes of erosion, the processes of creating oxygen in our atmosphere. Oxygen wasn't always a key component of our early atmosphere. Our early atmosphere was made up of hydrogen. I'm trying to think of some other. But we know now that our current atmosphere is made up of roughly 79% nitrogen, 20% oxygen. But initially, the processes that created that added oxygen, is what we're talking about in terms of uniformitarianism. And so what we can do, if you look at here, plate tectonics, the moving of the plates, so what happens then are the same types of things that will happen now. So the example that your book uses, and I really like this, the book uses an example of a mountain and a valley. So there's a mountain and the valley's right beside the mountain. And if you were to take soil sample of the valley and go up and take soil sample at the top of the mountain, some of the same sands, silt, and materials are found. So what that tells us, that in the past, that the top of the mountain was actually the bottom of a valley at one point. And so that allows us to, now this assumes that there's no input from humans here, okay? So one of the examples that I can use here, human actions. We talk about global warming. And I think most scientists are in agreement that there is warming occurring. The data shows that. Where scientists disagree is the cause of global warming. Is it what we call anthropogenic, which means caused by humans, or is it just a natural cycle? So anytime you have human actions that are causing consequences for the environment, this is breaking up what we call uniformitarianism.
Okay, we're going to talk about a concept that is sometimes difficult to understand, and that is the idea of the GAIA hypothesis. And the GAIA hypothesis was put forth by a scientist named James Lovelock, and he was working for NASA, and he was coming up with a method to look at other planets and see if you could tell if there was life on those planets by looking at the planet and using the light coming from the planet to estimate what the atmosphere was made of. And in a moment of insight, he thought about what it would be like to look at the Earth from another planet and realize that you would see the clouds and all the gases and recognize that all of those gases in the atmosphere came from living things. And he had this idea of the GAIA hypothesis, that the Earth behaves like a living thing. It maintains its own homeostasis, mostly its temperature, and it keeps it constant. So it's like a living organism, but it's not a living organism because it's not autobiotic, it's not self-replicating, but it does maintain homeostasis just like your body does, or like any living cell does. It maintains its own internal temperature in this case. And he began to think about, well, what does that? And it's kind of a chicken and the egg question, because we often think of life evolving on Earth, and the Earth was here first, and the geology of the Earth was here first. the rocks were forming and volcanoes were happening and spewing into the atmosphere, making the atmosphere, and that was making weather and storms, and water was in the atmosphere, and there were gases in the atmosphere. And then once that was there, life evolved. And once the life was there, then it was just responding to the environment. So we have the Earth kind of happens, thinking geologically first, then life evolves as a response to the geology, to the rocks, to the air, to the weather, to the water. And then any changes in that change the life. And Lovelock came along and said, well, wait a minute, maybe they're in concert together. So that's where the idea that what came first, the chicken or the egg, the life or the planet. And so consider we have our animals. Here's our squirrel, and our squirrel is breathing out CO2. The plant takes in CO2. The plant is breathing out O2, and the animal takes in the O2. Some of the CO2 goes into the atmosphere. Some of the oxygen goes into the atmosphere. The animal is also breathing out water. The water goes up into the atmosphere. The rain comes down as water, and the water goes back into the plant. And then the animal eats the plant and gets some of the water as well as some of the proteins. And so they are all interconnected with each other. And not only are the plants and the animals interconnected with each other, but they are in interaction with the atmosphere. And as the Earth gets covered with plants and with ice, things like that, that reflects heat. And that cools down the Earth. And life responds by evolving animals and plants that can survive a cooler planet, or the amount of plants reduce, or the amount of ice changes, and more heat can get absorbed, and that raises the temperature a little bit. And so we end up with the Earth is governed by a thermostat and maintains homeostasis. And so we have the temp, and it rises, and life changes and evolves based on how the temperature changes, and then that might lower the temp a little bit and keep it constant. And the Earth has remained surprisingly constant in temperature. There's been fluctuation with ice ages and whatnot, but within a fairly narrow band that supports life. And so we see this as a negative feedback loop, just like we've talked about before. And so the Earth maintains its own homeostasis through a negative feedback loop. And that idea that it maintains itself as a complex interaction between the living Earth and the geologic Earth, that has been called the GAIA hypothesis by James Lovelock.
When I first thought of the Earth as a self-regulating system, it was in 1965, over 40 years ago, and it slowly evolved in my mind over the next couple of years or so. And I used to live in those days in Wiltshire, in the village of Bowchalk, and a near neighbour of mine was the famous novelist William Golding, who subsequently got a Nobel Prize for his writing. And he was a close friend of mine, and we used to often to walk to the village shop to get things or post our letters. It was also the post office. And he would quiz me about what I was doing in science, because he was very interested in science, although he was a literary man. And I told him about this idea of a self-regulating Earth. And he said, well, you better give it a proper name. Too big a theory just to be some scientific acronym or something like that. So I suggest you call it GAIA. Since I introduced the concept of GAIA, it's gradually become mainstream science. They never talk about it as GAIA because the biologists scorned it so fiercely in the early days that most scientists are scared of using the word. So they talk about Earth system science, but it's the same thing. And we now realize that the Earth does regulate itself, and we know quite a bit about all the various systems. You see, it's a good theory. It's made no less than 10 predictions that have come true. And that's good going for any theory. For example, we now know through Gaia theory that the clouds over the great ocean areas of the Earth are produced by organisms living in the surface, the algae. They produce gases that go up into the air, oxidize, and produce the nuclei around which cloud droplets form and reflect sunlight back to space. The Earth would be perhaps 10 degrees hotter were it not for the existence of those clouds and the organisms that produce them. We also know that the removal of carbon dioxide from the air would not take place at anything like as fast as it does were it not for the organisms present in the soil and on the rocks and everywhere around the Earth and in the ocean as well. And those twin processes, reflection of sunlight and pumping down of carbon dioxide, are what keeps the Earth regulated. If there were no life on Earth, and this is such an easy calculation, you can practically do it on the back of an envelope, you would find that the Earth's temperature would be well over 60 degrees Celsius throughout. I have no personal doubts about the validity of global warming. There are not only are there specific events, odd events, that have happened so rarely in the past that they're extraordinary, but there's a concatenation of them, one after another happening, that the man in the street notices. Ask almost anybody if they think the climate's changed in the last couple of decades, and they'll all say yes, and give you lots of examples of why. I mean, just think of here where I'm living. People are talking about growing olives in Devonshire. Would you believe it? Wine is grown all over the place now. There's even vintage British wines. It's the whole thing is changing, and changing in a way that the man in the street notices. However, to add to that, we're nearly all urban now, and we live in air-conditioned houses and cars and so on, and we don't see anything as much of the environment as our ancestors did. Well, and because of that, we've lost touch with the natural world and are unaware of the changes that happen in it. Global warming is much more than just a real effect. It's something deadly that will threaten nearly all of us who are now alive on the Earth by the end of this century. The climate right now, if we'd never developed as an intelligent species, would be probably moving slowly back towards the next glaciation. There's some debate about that. Some think the present interglacial would have gone on a bit longer this time, perhaps as long as 50,000 years. But sooner or later we'd have gone back into an ice age again. Now we will not. By putting all that much carbon in the atmosphere, we've irreversibly changed the Earth so that it won't go back to another ice age, not at least for another 200,000 years. The climate change we're seeing now is closely similar to a geological event that occurred 55 million years ago at the beginning of the period the geologists refer to as the Eocene. What happened then was, we're not quite certain how, but something like 2 million tons of carbon dioxide came into the Earth's atmosphere over a period of about 10,000 years. And I think the most likely cause was a volcanic sill, lava underground from a volcano coming up beneath a petroleum deposit which was in what is now the Norwegian Sea. And this vaporized practically the whole of the deposit and put this huge quantity of carbon into our atmosphere. Well, when you ask about 20 to 30 years ahead, I can speak not just from my own view, but from the expressed opinions of senior climatologists who have represented their thoughts in the Intergovernmental Panel on Climate Change's great reports. The most recent was in 2001, but one is due next year, the update, and I've seen it. And what it says is this, quite simply, and it's very stark, that by something like 2040 to 2050, the European excessive summer of 2003, when over 20,000 people died of overheating, will be the norm. Every year will be as hot as that, nearly. Now, the consequences for people might be dealt with. They may go away for the summer to cooler places, or they can turn up the air conditioning. But for the plants and the ecosystems, there's no such relief. And the probability is that European agriculture will cease to produce food by then. It'll become a desert and scrub region naturally. That's not very far ahead. So where do the European people get their food? Because the rest of the world will not be exempt. Asia, America will all be suffering the same consequences, as will Africa and the other nations of the southern hemisphere. We will be entering a world where supplies of food becomes more and more scarce, and there will be mass migrations. Anyone with an imagination can see the awful human consequences of that, and we're talking about something which is only about 30 years ahead. If we follow the 55 million years ago precedent, temperature rise will now be levelling off as the Earth system, what I call GAIA, takes control. Just like when one of us gets a fever, our temperature doesn't go up until we become roast meat. It levels off at a higher level and after a while sinks back again. Same's true of the Earth. Many times in the past, when there have been catastrophic events, that it's had a fever and its temperature has gone up, but never to totally destructive levels. We wouldn't be talking about it if it had. And so that's what I think will happen. It'll level off towards the end of the century at about 8 degrees warmer than it is now. That's a huge change when it's looked at on a global basis. And it takes us to a region that humans have never experienced before, a state that it will be likely to last at least 100,000 years. I happen to think that there are too many people on the planet now. I think Malthus was right. You see, he wrote his famous treatise in 1800. At that time, there were only 1 billion people on Earth. And if his advice had been followed at that time, and all the great green ideas of sustainable development and renewable energy and so on had been applied then in 1800, we might have escaped the mess we're in now. Perhaps not all of it, but a great part of it. But we didn't. We went on increasing our numbers. I think that now 6 billion plus on Earth is quite unsustainable in any sense. Our giant mistake was combustion, learning to burn things. At first it was harmless just for cooking, but we never stop at that level. We start doing it on a grand scale, like burning down whole forests, because you get cooked meat a lot cheaper that way. There's much less effort. And that was our mistake. And we've been making the mistake for a long time, and we're only just beginning to discover how serious a mistake it was. Remember, it's not just modern man that's damaging the planet. The first people to move to Australia during one of the previous ice ages, a long time ago, managed to destroy almost the whole ecosystem of that continent with just quite simple tools, fire drive hunting and tricks of that kind. So we're a pretty unpleasant species in many respects, and always have been. Modern man is just more efficient at doing bad things. I think we are, as a consequence of global warming, going to have a major mass extinction of life on Earth. And if you include numbers, it'll be an extinction of humans too. I don't see more than, at the very best, 20% of us surviving through, maybe a lot less than that. And it's a very interesting question, because the event 55 million years ago was not a mass extinction. There was very little extinction of life, even though very much the same things happened. And the difference was that pollution of the atmosphere naturally took place over 10,000 years, and organisms had a chance to migrate to the cooler polar regions, where they survived throughout the 200,000 years of heat, and then they migrated back. We are doing it so rapidly that organisms don't have time to get up to those regions. They're not doing badly. It won't be a total extinction. It's quite surprising that the doubters of global warming will still comment on the fact, isn't it remarkable, I saw in my garden a hummingbird hawk moth last week. It must have flown up from Africa. Why? It's flown up because it's so much warmer here now. It's a habitat. I'm not a nuclear fanatic. I don't think it's the right answer to make the whole world nuclear. That's going too far. I think we have to use the energy we have available that is efficient and that will give us what we need with the minimum damage to the planet. And for densely populated countries like Japan, Britain, Germany, and many other European countries, nuclear energy is almost ideal. It's got a minimal footprint on the Earth, and yet produces huge quantities of electricity at a very reasonable price that everyone can afford, and will keep cities going. And never forget, where urban people and a modern city like London or New York would convert to a camp like one of those in Darfur in 1 week if electricity was switched right off everywhere. I think that nuclear has got to evolve in the way all energy systems evolve, and I'm very pleased to see that the latest nuclear plants, and one is now being built in South Africa, are small-scale plants that just provide enough electricity for a small region. They're the so-called pebble bed reactors. They're quite small, quite safe, and very suitable. And that kind of evolution always goes on in engineering. We should remember that the very first nuclear reactors in the world that supplied energy were built in this country, Britain, in the 1950s, in 3.5 years, just from drawings. That's all it took, and one or two of them are still working. Personally, and I'm supported in this by no less a dignitary than Hans Blix, who said about 2 years ago, "What's all this fuss about nuclear waste? There's hardly any of it, is there?" And that is the point. Last Christmas, my wife and I were invited to Sellafield, which is the British depository of all nuclear waste practically so far. And we walked around at the plant. It's quite a pleasant plant to walk around, and found that the radiation level, with a handheld monitor of mine, not one that had been supplied, was about the same as it is here where we're sitting in this room. In other words, completely safe. Around the building, which was not very large, where 40 years of all of Britain's nuclear waste, civil and military, was stored, the radiation level rose to just above that in the streets of St Ives, a town about 60 miles from here, that happens to be in a rather uranium-rich bit of soil. Still absolutely harmless. Now, all of that waste in that building, and it wasn't a very large building, it was in the form of blocks of glass that had been fused. What is the problem, I ask? Now, when you compare that with the carbon dioxide waste, each year we produce, if you froze the carbon dioxide or fixed it as they want to do into something like magnesium carbonate, it would make a mountain 1 mile high and 12 miles in circumference every year. Now that is truly deadly and will kill nearly all of us if we go on doing it. So what on earth do you want to fuss about nuclear waste for? If you go to France and much of Europe, you are riding in trains that are powered by nuclear electricity everywhere. French have been very sensible. They run almost everything on nuclear. The very Greens who scream about the dangers of nuclear have homes, second homes in France. They're mostly wealthy people. They don't seem to notice it there. Such is the perversity of people. No, but you couldn't have a nuclear-powered car with a nuclear motor in it. That's ridiculous. But what you can do is run it on batteries, and it won't be long before they're all running on batteries, and they can be charged from nuclear electricity. So that's the way it would go. Planes will take longer. I think that the so-called alternative energy schemes like wind, solar power, and so on are pretty inefficient and impractical and no solution to our problems at the moment. And I think they're dreamt up by urban people who want to do something natural. They don't like anything industrial and feel that they're doing good. But they're not. That's not a way to run a country or a world. There are some what you might call natural power sources like hydroelectricity that are excellent. Why not use them? Norway largely runs on them. And if you've got hydroelectricity, use it. But the sad thing is we've used about all we can. There isn't any left to spare. One day maybe we can get energy from tidal sources. And I do wish the British government had the sense to build the so-called Severn barrage. That's a power scheme across the estuary of the River Severn in western Britain that would provide the output of 4 major nuclear power stations. But there were too many arguments about doing it, and I'm afraid the Greens were the main objectors. They thought it would upset a wildfowl habitat somewhere or other, so it wasn't done. There is a nuclear power station not too far from here at a place called Hinkley Point in Somerset. I think our benighted government, over-influenced by Greens, may well let it shut down in, I think, even as soon as next year. If they do, it would require 3,200 giant turbines to replace it, and they would only work when the wind blew, which it doesn't very often. Hinkley Point has provided most of Devon, Cornwall and Somerset with electricity for the best part of 30 years without any problems whatsoever, so why close it? As a scientist, and one who when I was young read science fiction, that question, are we likely to be able to do anything about it by engineering or science, really fascinates me. And there are a lot of proposals up at the moment. Some colleagues of mine in NASA at Lawrence Livermore Laboratory have what seems a very reasonable scheme for putting up sunshades in space that would be at the gravity neutral point between the Earth and the Sun, so that it wouldn't take much effort to hold it there. And it would be a carbon fibre diaphragm spun out, I've forgotten the diameter, but quite large, 10 miles at least. And it's not impractical. They say it would cost less than the space station, but it would disperse about 2% of sunlight coming in and relieve us of global heating. Now that's one proposal. It would take a lot of time and a lot of politics to get it working, but it might happen. Another much more practical one is that we could mimic the great volcanoes. When Pinatubo went off in the 90s, it set back global warming for 5 years, stopped it happening, just because of the aerosol of tiny particles of sulfuric acid in the stratosphere reflected sunlight back to space. Now, Russian scientist Bodaiko suggested we do that as long ago as the 1970s to alleviate global warming, but it wasn't taken up then. But it is beginning to get taken up now as a serious proposition. It would be quite easy to do. I would like to see it done by just getting the main airlines that fly commercially around the world to do the deposition of sulfur in the stratosphere as they fly. For example, if engineering allows them to burn sulfur-rich fuel, unrefined kerosene instead of the highly refined stuff, that would do it. That would put enough sulfur in the atmosphere to give you a Pinatubo every couple of years. It's all very well for wealthy urban people to say that everybody ought to drive a hybrid or something small, but the average person can't suddenly go out and buy a new car. They're lucky to get their old banger going to and from work. There's a lot of impracticality here. It takes an awful long time. And how do you tell the Chinese to set back the aspirations of their people and stop building coal-fired power stations? They build one every 5 days, believe it or not. It's a very impractical suggestion to ask people to cut back on carbon sufficiently to have a big effect on the world in time. This is it. Time is the essence of everything. So I think those notions of amelioration, like sulfur in the stratosphere or sunshades, are worth pursuing because they will buy us time. But there's a big but. Think of them as like if your kidneys fail, you can always go on dialysis. And who would refuse dialysis if death was the alternative? But it's only going to buy you time, that's all. When you ask the question, have we or when did we reach a tipping point in global heating, I think we've passed the point of no return myself, but it's only a speculation. I can't give you firm figures on it. Others think it will be a few years ahead, but whatever way you look at it, it's pretty close. The long-term prognosis for planet Earth is, strangely enough, more clear-cut than the short-term prognosis, because, you see, the sun remorselessly warms up. We know pretty well how it works, and it's got a greenhouse problem, just like the Earth. It burns hydrogen by fusing it together, and the product, the ash, is helium. And as helium accumulates in the sun, just as CO2 accumulates in the Earth's atmosphere, it acts like a greenhouse gas and makes the middle of the sun hotter, so the hydrogen burns faster. It's as simple as that. The sun is warming up. And as it warms up, life on Earth becomes more and more difficult. And we reckon in 1 billion years, the output of the sun will be putting 2 kilowatts of energy for every square meter of the Earth's surface. And that's more than the system can manage if it's a carbon-based life system. And that's the end. However, long before that 1 billion years is reached, shall we say 500 million from now, some catastrophe, like a planetesimal impact, will put such a stress on the remaining ancient Gaia, so to speak, that it will crash them and go to its dead state, like Mars or Venus. Everything in this universe is mortal, even stars, even galaxies. They're all mortal. It's part of the name of the game called the second law of thermodynamics. Everything runs down, grows older and dies. And if that seems gloomy, think of it the other way round. If it weren't doing that, you wouldn't have any energy to do anything. We have to adapt. Adaptation is the thing humans have to do, and the thing they most have to remember is to try and preserve civilization. That's our most precious assets, and we're a huge benefit to the world that way. We tend to think of ourselves as some sort of plague or destructive agency. We are, but at the same time, we are something wonderful. After all those 3.5 billion years of evolution, the Earth at last has something with intelligence and communication, which is part of it, because we're part of it. We're natural. We shouldn't think of ourselves as separate from the Earth. And through our eyes, the Earth has seen for the very first time from space what an incredibly beautiful planet she is. And that's worthwhile, well worth it.